Hello everyone, I'm Jinsheng Wang from PKU. Today I'm going to introduce our work named a Keypoint-based global association network for lane detection. This is an outline of my report this time, which is mainly divided into 4 parts. Lane detection is a challenging task that requires predicting complex shapes of lines and distinguishing different instances. Earlier anchor-based works regress predefined anchors into various shapes of lines, which lacks enough flexibility to fit complex shapes due to the fixed anchor shapes. Lately, some works propose to formulate lane detection as a key point estimation problem, and group adjacent key points being to the same line in a point-by-point manner, which is inefficient. In this paper, we propose a global association network to formulate the lane detection problem from a new perspective, where each key point is directly regressed to the starting point of the line instead of a point-by-point extension. In addition, we further propose a LFA module, which adaptively captures local collaborations between adjacent key points to supplement local information to the global association. This is the overall architecture of our GNet. The goal is to predict a collection of lanes with each lane being donated with key sample key point at this. During the training phase for key point estimation head, we adopt penalty reduced fork loss to deal with the imbalance between key point regions and non-key point regions. For the offset head to distinguish different instances, we use the starting point to represent each instance uniquely. Instead of regressing the absolute coordinate directly, we regress the offset from each key point to it, which can be defined as this. L1 loss is used to constrain the offset map. To obtain the starting point of each lane, we select key points whose values are less than 1 on the offset map. By this means, the instances of all the lanes are determined with their starting points. Afterward, we associate the rest key points to their belonged lanes according to the estimated offsets, which is shown in Figure B. Each key point estimates the coordinate of starting point as follows. As shown in C, key points that point to the neighborhood of the same starting point are grouped to produce a whole line. The above are done by matrix operations to ensure parallel association. We propose the LFA module to enhance the local feature representation of each key point. Take a specific key point as an example. We first use a convolution layer to predict the offset between it and its surrounded M key points on the same line. Afterwards, features of adjacent points are integrated with a deformable convolution to aggregate context at this. Then, a matching needs to be established between the PI and the GI. We search for an assignment with the lowest matching cost. Hungarian algorithm is adopted to efficiently compute the optimal assignment. Smooth L1 loss is then applied to surprise the prediction of adjacent key points. We conduct an ablation study on the CU-lane dataset based on the small version of GNet. As shown in the first row, LFA makes correct prediction even with vehicle occlusion. From the second and third rows, LFA is able to suppress background noise, which may be introduced by global attention. In Figure 7, with the addition of auxiliary losses, LFA can predict the aggregation points around the line. It is demonstrated that LFA is robust in its understanding of the local structures. This property contributes to the enhancement of features and the suppression of the background noise. Our GNet achieves the sort-time results on CU-lane and ToSimple, especially in curve scenario, which shows a superior performance efficiency trade-off and great potential. Thank you for your listening. Our code will be available at this link.